I'd like to welcome all of you to the next session, which is on big data analytics in aerospace. And this is a new area that we're going to be discussing today in our panel. We have a very distinguished panel here. I'll go through each person in detail and talk a bit about the reason that we're having this panel. So if you look at what's happening in industry outside of the aerospace world these days, you'll find that big data, analytics, and data science, and all of these kinds of terms are being hotly used, and they're being used in a wide variety of contexts. You'll see that there's a huge demand for people who are working in the field of data science, big data, analytics, machine learning, and so forth. And the reason for it is that people are starting to see that there's a tremendous source of data out there, for example, in social networks, on Facebook, on Twitter, on Google, and other types of platforms that's generating data. And that data can be analyzed and mined in order to create new insights that can be eventually turned into revenue streams. And because of that, there's a tremendous amount of interest in big data and analytics in the broader world. Now, here we're working in the aerospace domain. It's not the world of social networks. It's not the world of Twitter or of search or some of these other areas. And yet we're talking about big data and analytics. Why is that? Well, it's because a lot of us feel, and I'm sure many people in the audience also resonate with this, that the underlying theme of taking data that might be coming from distributed sensor networks on an aircraft or across multiple aircraft, taking data from other sources, for example, text information about aircraft or about spacecraft, taking data from other sources that might be weather-related, and putting it all together and analyzing it all in consonance can produce new insights. And those insights might have some benefit for safety issues, for reliability, resiliency, and so forth. The concerns that we often talk about in aerospace. So today in this panel, we're going to be discussing, first of all, what big data and analytics is, what some of the key pillars are of that area, and how big data and analytics could be applied in the aerospace domain. Now, having said that, I wouldn't want to give the impression that it's never been applied. Obviously, major companies, government, academia, industry, they've all applied big data and analytics in the context of aerospace. But the challenge is, how do we take that from where we are today and really bring it into a new era where the information system itself is the foundation, it's the underlying infrastructure on which we build an aerospace system. So if you think about it, a lot of us have realized that there are certain pillars in aerospace engineering. For instance, structures and propulsion, aerodynamics, control. These areas are well understood to be foundational elements for the field of aerospace. But also, we'd suggest that information systems is another thread, another important pillar of this type of engineering. And so we'll be exploring that as well. My name is Ashok Srivastava. I am the editor-in-chief of the AIAA Journal of Aerospace Information Systems. I took over that post about 2 years ago or so. And the primary focus of this journal is to work and to publish documents, original articles in the field of information systems as they pertain to aerospace systems. So it's not a computer science journal, for instance. You wouldn't see things in there about search algorithms or about social networks or something like that. But you will see papers there about how to take data from aerospace systems, analyze it in order to uncover new insights. Or how to take data from multiple sources and fuse them together in order to get a bigger picture of what's going on, let's say, in the air transportation system. Those types of papers you'll see, as well as a myriad of other papers in areas like verification and validation of complex systems. You'd see papers in human automation interaction. Wherever the notion of information, the notion of data, and the notion of an aerospace domain comes together, somehow you'll find that the JAIS, Journal of Aerospace Information Systems, has an article in there. So I'd welcome any and all submissions of original research to the journal. Let me take you a little bit through our panel. So I'm very, very pleased, by the way, to have the panelists here with me. Professor Eric Ferron from Georgia Tech, an eminent scholar in many fields related to aerospace engineering, but particularly one of the reasons I wanted him to attend is because he can provide us with a big picture view of what some of the challenges are in information systems as they pertain to aerospace. We're very fortunate to have John Kelly here, technical lead from data analytics at Lockheed Martin. He'll talk to us about the work going on there in the area of machine learning and how it pertains to aerospace systems. Similarly, we're very fortunate to have Melanie Lorang, who's an associate technical fellow at Boeing, and she's going to give us a big picture view of what's happening at Boeing in the area of analytics. I'm very excited about it because a lot of us have spent a good deal of time thinking about how aerospace systems could be influenced by information systems, and I think both John and Melanie are going to give us a great introduction and overview of what's happening in those areas. We're also very fortunate to have Nikunj Oza, who's from NASA Ames Research Center. He leads the data science group there, and he'll talk to us most likely about the work that's going on there, as well as some of the other challenges that are facing information systems and big data, as well as the field of aerospace. So I'll just set the stage here, talk about a few challenges, and then I'll turn it over to the panelists. This is, the first part of our panel is meant to be just introductory, but then we'll be turning it over to you, the audience, to start asking questions, and we can create a dialogue. So this is by no means meant to be a single line of communication from us to you. But I wanted to give an idea of what big data means. Frankly, when I heard the term many years ago, it jarred me a little bit. And the reason is it's a rather strange set of words to put together. Big data, it sounded extraordinarily informal to me, let me put it that way. But it has become the term of choice in industry. And what does it refer to? It refers to 4 characteristics. One, that data is coming in at high volume. And you can set the volumes however you'd like. Here, they're saying, greater than 100 terabytes. We're dealing with systems where I work with many petabytes generated per day, just a lot of data. Velocity, that the data is coming in rapidly. It's not trickling in bit by bit, but instead you might be having many, many observations coming in per second, and also many, many data streams. And that poses an interesting challenge if you think about it, because you can't take all of that data and just store it somewhere and then hope to analyze it on an ongoing basis. Instead, you might have to create new algorithms that can deal with streaming data. So it puts a new constraint on the system. Next, variety of data. So we often think of data as being measurements, so continuous measurements of weight or of temperature, pressure, something like that. But data obviously can have many other kinds of forms. It could be free text. It could be what the pilot wrote in an ASRS report, an Aviation Safety Reporting System report, about what happened yesterday when he or she was flying the airplane from LAX, right? That's another form of data. It's unstructured, but we would like to be able to analyze that as well. There's also the notion of semi-structured data and categorical data and so forth. So we want to have a broad understanding of what data is. So there needs to be variety there. And then variability in the data. What you think the data means today may not be what it actually means tomorrow. That can happen, and when that happens, there's variability in the data. And so creating systems that can deal with this kind of thing, velocity, volume, variety, and variability, is one of the hallmarks of a big data enterprise. Variability. So a very topical example here. In the past, I worked at NASA, and one of the areas that we worked on was the so-called PRACA system, which was built for the space shuttle. And this was a problem reporting system, and there was a certain database structure that was created to house that data. This is also true for ASRS. Now, what happens is that we start off with the system, and we say, here's a column. I'm going to identify the column. And the column means engine variation. I'm making it up. I don't remember that that's actually a field in that data system, but I'll call it engine variation. So what I mean by engine variation today is, let's say, deviations from nominal RPM. Now, Eric here takes over. I retire. He takes over. And he says, you know, engine deviation means something, not only RPMs, but it also means another type of deviation, another type of anomaly. He may not be recording the RPM anymore. That might be lost, but it might be high, medium, and low pressure, let's say. It's another kind of engine deviation. And so that kind of variability can get introduced. In this case, if there's just two people, hopefully we can document and get it over with quickly. But there can be situations where that variability comes in simply because of the nature of the sensors or the nature of the data that's being collected. So that variability introduces a great deal of difficulty when you go back and do historical analysis of the data. Now, another key thing that has happened in the field of big data that I wanted to illustrate here is that there's been a fundamental change in the way people store and analyze data. So you all are, I'm sure, very familiar with flat files. These are just the files that data can be organized in that sit on your laptop or sit on your mainframe computer. And it's a single file with rows and columns. It's essentially a matrix, right? It's the simplest data structure to work with. It's a very powerful data structure to work with. One level of complexity beyond that is to create what we call a relational database. So now the data is not just in one table, but it's in many tables, and you join them together and you analyze them. And so Oracle and Microsoft and IBM and many other companies have created relational databases, and those were the engines, those were the workhorses for data systems for many, many years. There was a whole revolution in business intelligence that was focused on that. Now, what's happened, though, with the advent of companies like Google and Yahoo and others, is the creation of a new type of system, which, in contrast to a traditional database, which is a shared system, this is a shared nothing system. So nothing is shared. There's no proprietary hardware. In fact, there's no proprietary software for the most part. So what that means, instead of a company going and spending a lot of money with some vendor and saying, here's $1 million, please give me a database, here you go to a code repository, you download it, and now you have a system that's running on commodity hardware, that is running on a system that requires no sharing, and that also requires no licensing fees. So this is a big deal. If you're running a major data enterprise, this is a big deal. And for aerospace, it's going to be an important deal. It's a distributed system, so it's no longer centralized. That poses some interesting challenges for the area of machine learning that we'll get into in a little bit. It allows for massive parallel processing and a new system called Hadoop, which you might have heard of. So if you haven't heard of it, type it into your favorite search engine, and you'll find a huge number of articles written about Hadoop. What is it? H-A-D-O-O-P. And it's named after the founders, the founder of the idea. I think his son or daughter had an elephant, a baby stuffed elephant. And the name of that was Hadoop, and so he therefore named it the system after it. It's an extraordinarily powerful system for dealing with large amounts of data. And the underlying, one of the key underlying techniques that you'll find in Hadoop systems is something called MapReduce. And I won't go into MapReduce in general, but what it allows you to do is massive parallel computation very quickly. It's different than the kind of parallel computation you do in a CFD calculation, but it's still a very important type of calculation for doing search and for doing other kinds of optimized queries on massive data sets. In the big data innovation, it also allows for very low cost of storage. So instead of paying, again, some hardware vendor and software vendor a massive amount of money to store this data in a proprietary system, now you buy extremely cheap hardware, and you assume that it's going to fail, but you buy a lot of it, and then you put your data onto it, you have redundancy, and then you move with it. This is the way major data systems are being built today. It's very different philosophy than the philosophy we often see in aerospace systems, and for good reason. And there's a cultural challenge there that we'll talk about as well during our panel. So what are some areas of application? I've only listed 5 here. areas. There are many, many more. I don't mean this to be a complete list. But if you think about our keynote speaker this morning, he spoke in some detail about the need for understanding cybersecurity and the way that relates to aerospace systems. This is no doubt one of the key areas that we need to address. It is a big data problem. It is an analytics problem. It has machine learning in it part and parcel. And we, as a community, can come together and work on it specifically for the aerospace domain. So this is not the same thing as doing cybersecurity, let's say, for a retail company, or for a telecommunications company, or for a search company. When it comes to aerospace, it'll have different characteristics. And it will be very interesting to explore that in our panel today. Understanding human automation interaction is another area that I think lends itself well to the big data realm. Understanding how people interact with complex systems like a commercial aircraft, how they fly those aircraft in various terrain, across different types of weather phenomenon, et cetera. That can be very valuable in different traffic situations. That can be very valuable. It lends itself very well to big data and analytics. The whole area of air traffic management, again, very important area for us to understand how big data and analytics can be applied there. Autonomous systems, in some ways you could say that big data and analytics are almost the underlying architecture that you need if you're going to create some level of autonomy. If you don't have the data, on what basis are you going to make a decision, right? And so that kind of information is going to be important for autonomous systems. Systems health management in general, if you think about aircraft and the way they're flown, or spacecraft, and the way those fly, taking information from those in real time, making decisions about the anomalies that might be on board, the diagnostics, prognostics, and then doing mitigation also falls into the realm of big data and analytics. So you'll see it's a very broad picture that we're trying to paint here. There are many more areas that we could focus on, but I wanted to set the stage here. Now I'm going to turn over to Eric, who's going to take us through a few examples, and then we'll subsequently go through the panel. Each person will present briefly some of their perspectives on the matter. And then we're going to move into a session where we'll have discussion amongst ourselves, and then most importantly with you all in the audience. I'd like this to be as interactive as possible so that no one gets bored, particularly me. Okay, so with that, I'll turn it over to Eric, and he can take us through, and you can
thank you very much, Ashok. So I'm Eric Brown. I work at Georgia Tech in the School of Aerospace Engineering, like a few of us at this conference. And I recognize quite a few faces. Many of them are actually turned towards new aspects of the aerospace sciences as we're moving towards new endeavors. So I just wanted to bring my perspective on big data. And it is the perspective of somebody who, whose first paper was about Kalman filtering, and who's never stopped looking at trying to transform data into knowledge. I would say that there are a few things that have changed with the advent of large amounts of data. For example, just to repeat some words I've heard before, I don't remember who said them. Usually when you do Kalman filtering, the A matrix is huge. You know, it has a lot of states into the system. Okay. On the other hand, the observation matrix is like fat but flat, meaning that there are very, very few outputs. Now we're facing a slightly different problems where the A matrix may still be kind of large, but the C matrix is now very tall. Okay, it gives you a lot of information about the system. In fact, so much information that you wonder what to do with it. Of course, the Kalman filtering framework allows you to deal with that as easily as if the C matrix was flat. Okay, but nevertheless, it still raises interesting questions. Like, for example, well, if my C matrix is that tall, maybe I should make the A matrix even bigger now. Okay, and because maybe I'm now able to observe things I was not able to observe before. And so we have some examples of that. For example, if I move to the next slide, here. Before I do anything, I must express my gratitude to my two partners in crime, John Paul Clark and Hamza Balakrishnan. JP talked this morning, I understand. I don't know if Hamza is around. But let me skip some of the material here because it relates to what Ashok already talked about. And let me bring the examples of airport analysis. So here was the story back in 1996, 1999. We had a big fat A matrix, okay, that was the dynamics of the airport, in that case, Logan Airport, okay. And I can tell you in terms of observation, we had very little. We did not even have a Google map of the airport. To begin with, Google did not exist anyway. And in terms of data, we had like very limited data in terms of understanding the dynamics of the airport from a taxiway perspective. Meaning that we had access to the time at which the aircraft landed, the time at which the aircraft reached the gate, the time at which the aircraft left the gate, and the time at which it takes off, which is kind of not very rich if you want to understand like the whole taxiway structure. Nevertheless, so in other terms, we had like a C matrix which were like pretty flat. You know, we had few observations given a fairly complex state. Here's what happens. But now if we go to, oops, how do I do this? Oh, okay. If I can start the movie or somebody starts the movie. Let's try again. Okay, now we have a completely different situation, meaning that the data that is available is like absolutely gorgeous. The old ASDE radar that used to be tracking all the aircraft along their motion on the taxiway system for the great enjoyment and safety, by the way, okay, because it was meant to be seen by air traffic controllers in the tower, especially during foggy conditions. Now those data are becoming available to just about anybody. The old ASD radar has been replaced by ASDX, which is a digital version of ASD, which gives you the position of aircraft in real time. Okay? If you don't have ASDX, you have also other triangulation systems that actually locate the position of the aircraft in real time as well. What does that allow you to do? Well, exactly what I said, which is the A matrix, which was like, which we chose to be very simple. Okay? In that case, it was just like before saying, well, the airport is like one arrival stream of aircraft, okay, and then one server, okay. So the arrival stream could be arriving aircraft, and the server would be the gate, or the arrival stream would be actually the aircraft leaving the gates, and then the server being the runway threshold allowed them to take off. Can now be tuned, of course, much better according to this data. But soon enough, of course, what Hamza did was say, hey, you know, if I know the position of this aircraft in real time, and with such high level of resolution, by the way, this is not Boston anymore, this is LaGuardia, then why don't I start looking into more of the details of the airport? So what happened is the A matrix suddenly became a lot larger because we could afford a lot more, we have a lot more resolution. And what you end up is with that multi-queue model of the airport that Hamza has been calibrating over the past couple of years, which will allow us eventually to do control of the airport at a much higher level of resolution with significance. If you remember the old saying, you can, you know, there is a big difference between high level of detail and high accuracy. Sometimes you can have like very high level of detail models of what happens, and then the models are completely inaccurate. On the other hand, you can have very low resolution models that are perfectly accurate, okay? Among students, it's a big mistake to mix the two. But here, thanks to sort of this stream, increasing stream of data that's becoming available to us, we can actually make sense of developing more detailed models that are actually tuned by better and quality and larger quantities of data such as the ones I mentioned. Okay? I just want to raise another point. As a user, I've been listening to a lot of people, including Ashok, Nikunj, with whom we worked over a couple of years, and also some of the friends I've been having in Europe. let me go to this next presentation. One of the things that people have been wondering is in terms of manipulating and transforming big data into knowledge. Well, one of the differences between big data and, say, the kind of data streams you get out of the trajectory of an aircraft is that big data can actually represent something a lot more complex than, say, a single aircraft trajectory. And when you have a very complex system, you can do either one of two things. You can sort of put in a framework where you sort of garble the whole picture by saying, yeah, it's a highly complex system for which you're going to develop fancy method, or you can go the practical way, or the more pragmatic way, saying, well, so okay, I have complicated sets of data. These data carry a lot of knowledge, and the human is very smart. So why don't we sort of mix when we need to interpret those data? Why don't we just share the work between the human, who has a lot of good ability to classify things and to recognize patterns, okay, or to actually decide that is a pattern, as opposed to sort of have a predetermined library of patterns and then say, okay, this is the one that fits the best, and then combine that with the processing power of computers. And so what we've been seeing is among the tools available, tools that really allow us to sort of capture what I would call like the highly nonlinear discrete effects that are characteristics of systems that generate large amounts of data, be it the air transportation system, telephone networks, et cetera, and sort of come up with the best of both worlds. So in this particular case, what we did is we played with a tool named FromDaddy, which came from the National School for Civil Aviation in France. And we used that tool to sort of test out a few things and sort of extract the data we want. In this particular case, what you have is an overall map of the Cleveland traffic, and we needed to isolate the traffic that would be actually bound to some of the airports there, either Cleveland, Detroit, Pittsburgh. And so you can either sort of write an algorithm that will sort of look for the airplanes that go to a certain altitude, or below a certain altitude, and eventually they're bound to a particular airport. Or what you can do is just like with sliders adjust and filter all the trajectories that don't go under a particular level. And by hand, you can very quickly convert the picture to the left to the picture to the right, where you have already done by hand in about 3 seconds, isolated the traffic that you care about. In this case, the traffic in Cleveland Center, which actually lands at or takes off from airports located in that center. Okay, so that's another thing that we noticed that was extremely useful. Another thing that we noticed by using tools aimed at manipulating large data sets is that there is a whole lot of techniques that are out there that really are a lot smarter than we thought, even without the help of humans. So let me go back a second and give you some idea about this. So this is, again, the Cleveland Center, which many people in air transportation love, because it happens to be like one of the gateways between the East and the West, okay? And gateways, but also bottleneck. And so what we see here is we wanted to sort of make sense out of the picture to the left, which is the traffic that we have crossing from one end of the center to the other end of the center. And we wanted to sort of extract like some meaning out of this. Okay, we were talking about meaning before. So what does meaning mean? Well, it means we want to go from data to some sort of a model that I can repeat, et cetera, et cetera. And what we got on the picture to the right was a particular data clustering technique named kernel density estimation based on edge bundling, and which actually transformed the picture to the left, which was like a whole cloud of trajectories, kind of messed up. As you said, I think we fit within your sort of million of data point paradigm here. I mean, we got this is a big data set. And we ended up by a purely geometric algorithm that knew strictly nothing about air transportation, with sort of the more discrete structure you see to the right there. And when we presented that structure to the right to the air traffic controllers, they say, oh yeah, that's exactly what we do. They say, yeah, I can count about 120 main flows there, and these flows are exactly those that we think about when we think about this center. Okay, so we can really reconstruct some information. Now, the fascinating thing about this big data world, and I will stop here, is to say that it also opens up some interesting views on how to model things. So if I'm going to go backward for 1 second, you saw that there was an orange grid that disappeared. I'm going to make it reappear in a few seconds. But before that, I just want to bring something first. So the willingness of people to come up with flows such that they can categorize the flight, saying this flight is on that particular track or whatever, is a very classical view of the world that then feeds into fairly well understood models for air traffic management, et cetera, et cetera. Okay? Well, that said, we have this big cloud of data to the left. And we say, well, you know, maybe with such a large set of data, we can stop putting or stop wanting to put some kind of a discrete structure on the way the air traffic management system works. And instead say, why don't we do and build like a more probabilistic models of how things work. So here's how it goes. It's the result of some of our elucubrations with Ashok, by the way. What we do is we put a grid, okay, it's the orange thing there. We put a grid, and inside the grid, we sort of count just the distribution of aircraft, say distribution of headings, and distribution of speeds, okay? And then we sort of look at, as a function of time, at how, for example, a particular density in one of the boxes influences the density in some of the neighboring boxes. So that means that instead of having like a very discrete model, which is driven by the fact that aircraft fly along trajectories, et cetera, we replace that by a completely different kind of model, which is that of more like a Markov chain, okay, describing the airspace system in terms of probability distributions. So where do these things come from? Well, they wouldn't have come from our own reasoning had we not have had access to the massive amount of data in the first place. Because how would I think about you know, densities of aircraft in sort of small squares that decompose the airspace unless I could first generate the picture that's to the left? Okay, so in that regard, and I think that we are back to what I said earlier, which is that the amount of the data, the sheer amount of data that becomes available to us actually forces us to think and put back into question the way we model the systems that we are interested in, okay? Now, I can give you even an extreme about this. You may think, oh yeah, but this is for these air transportation system, blah, 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 you know, like large-scale systems that, but it doesn't have to do with my science. Well, so there was an example, which is the work of Michael Kirchendorfer now at Stanford University, whereby he actually modeled the way an aircraft flies by a Markov decision process, okay, like a purely discrete thing. Okay, not only that, but he is the architect behind the next generation collision avoidance system that we're all going to fly with, whether you like it or not, by around 2025. Therefore, not only are these large data sets useful to address problems that we could not address before, such as very large systems with distributed data sets everywhere that now become all available to us, allowing us to make the fusion of things that we could not relate before, we just didn't have them. But it also allows us to start thinking about even like the very traditional ways we've been dealing with traditional systems in a different way to come up with alternative and operational solutions to some of our most urgent problems. Thank you.
Very nice. Thank you. Eric? John?
Thank you. I don't have any. So when I arrived last night, I was almost immediately approached by one of my colleagues who asked, "Do you want to go to the launch tomorrow? We can watch from the base. We can get back in time from the for the conference." And I said, "Yeah, sure. That sounds great. Let's do it." And then after giving that response, I asked, what time will we need to leave for that? And said 3:30, and can you drive? So this is a perfect example of making a decision without first accounting for all of the information. And I say this jokingly, and of course I still went, and then the launch got aborted with T-minus a minute 21 seconds. But in all seriousness, this is the basic goal of data analytics, is how can you account for as much information as possible before making your decision. And this could be a business decision, it could be a design decision, it could be part of a technical capability, such as doing something like object recognition. And one thing that I would kind of like to distinguish is, we've talked so far some about big data. I would kind of like to distinguish big data from data analytics in the sense that, the 4 V's that were mentioned are extremely important, determining what type of compute infrastructure is required, and are very valuable in the more data you have, the more variety you have, the more sources. In general, you can identify more insights, more hidden relationships in the data. But at the same time, what I'm typically more interested in is the usefulness, the direct usefulness of the data. I like to use 3 more V's, which is value, veracity, and visibility. So, is the data relevant to the problem at hand? Is it somewhat complete? You're never going to encounter a data set that's completely free of corruption and missing values. And last, can I see it? Do I have access to it? And all too often, I feel like I've actually had someone come to me and say, I have this interesting problem, I have this data set that I think is relevant, but I don't know if it qualifies as big data. I don't know if this really counts. So I want to stress that while big data is extremely valuable, it's not a requirement to derive information and insight from what you have. Data analytics on small or any size data set, the main goal is to identify complex multivariable relationships that you wouldn't be able to find with traditional statistical or experimental or theoretical methods. And so this is an extremely powerful outcome if you know how to use it. My first major foray into data analytics and machine learning was in graduate school, where my dissertation was working on developing signal processing and machine learning methods for decoding neural signals for brain-computer interfaces. And this, you asked about variability earlier. Just as an aside, this is an interesting variability problem where you essentially you're trying to learn what the neural signals are doing, but at the same time, the neural signals are trying to learn what the machine learning algorithm is doing. So you have 2 systems that are adapting to each other, and you're aiming at a moving target. Essentially, you could end up in a situation where you're chasing your own tail. Right. So, this was something where, the first time that I was able to see one of our research participants who was paralyzed from the neck down reach out with the robotic arm and touch someone with it. That was not only an extremely rewarding experience, but it really got me excited about machine learning, about data analytics. It made me think, if it can do this, if it can take something as complicated as the human brain, and just by listening in on the signals, deliver useful, actionable information, then what else can it do? And the answer is a lot. And so some of the areas that Lockheed is working on with this, and again, the main goal behind all of this is to close the information gap. So any decision that we have to make as a business or as part of our technical capabilities, all too often we're forced to make that decision without a complete set of information. So how can we ensure that we have all of that in time to make that decision? So some of the things I'd like to mention, and these are just a few of the areas where we're working on this. First is predictive diagnostics, which you've heard a lot about, I'm sure. This is very valuable in the aerospace domain. This is simply the idea where, similar to what happens with cars. You know, a long time ago you would drive your car, and every X number of miles you would change the oil. Now new cars have a sensor in them that will light up and tell you, hey, you should probably change your oil. And that's not just based on the number of miles, that's based on driving conditions. And so by the same token, we can look at usage data of aircraft and predict when a part is likely to fail so that we can replace it in time, but at the same time not do useless replacements, and we're increasing the operational availability at a minimum cost so that we don't have, you know, warehouses full of spares sitting around. And, you know, moving on from that, I think the next step is moving to what I refer to as prescriptive maintenance. So taking that likelihood that a part will fail and translating that into, here's the repair that needs to be performed. This is what's going to keep the aircraft running. We're sure that this is the right repair, because in all honesty, that's an even bigger cost saver. If I can predict when a part's going to fail, that's valuable. But if I can ensure that I'm performing the correct maintenance to where I don't have to come back later and do it all over again, that's even more important. And finally, moving on from that, you can move to what I refer to as adaptive design. And this is essentially closing the loop with data analytics, and is a very difficult mathematical problem. But essentially, instead of being able to say, here's my large data set, I would like to predict when this event is going to occur, which is the typical way of looking at a machine learning problem. You want to be able to say, here's the outcome that I desire. Tell me what my data set needs to look like in order to get that. So that's where we're moving towards. That's where we would like to be. But again, that's an extremely difficult problem to tackle. Another area we're working in is air traffic management. We're doing work to more on the broader scale to look at the entire grid and be able to determine when a particular sector might be overworked. And so this is incorporating massive data sets, you know, from weather and air traffic and everything else to be able to determine when a particular air traffic control sector might be might need more workers or might not need as many. And a few other areas we're working on working with our customers to deliver mission and customer specific configurations and spares packages. So Amazon and Netflix aren't the only ones that are interested in being able to anticipate their customers' needs. That's again a very valuable area for us if we're able to determine specifically what our customer needs for their mission in the environment that they're operating. And then also, we have a number of efforts that are looking at how we can improve our internal operations. So supply chain management is a huge area of interest for our corporation that accounts for a very large percentage of our cost. So how can we use data analytics? How can we use the vast amounts of unstructured data, open source data that's out there to be able to identify problems in our supply chain? Where is there a risk? Where is there something that might disrupt our supply chain? How can we identify counterfeits? How can we identify parts that might have conflict minerals or hazardous materials in them. Because obviously that's a major problem for us if we have to come back and find that out after we've already got the part and have it installed. So we're also looking at how we can identify our programs, how we might be able to identify, keep them on cost, keep them on schedule, by again being able to predict ahead of time when we might have problems. And going back to the small versus big data analytics, this is again something where maybe we start with a small data set, and as we get success, we add more and more data, more information to it, to where our capability continues to grow. We continue to get more accurate predictions and broader predictions. And something like this, this again goes back to the variability problem, where you have to consider, where you're trying to prevent something from occurring, essentially you want to always be wrong. Because if you're right, you want to be able to take action to prevent that event from occurring in the first place. So again, you have a data set that is shifting based on the results that your analytics algorithm is creating. Another area that is of broad interest for us is the link between the human end user and our platforms. So this partially goes back to the brain-computer interface work that I mentioned. If we can be able to connect our users in some way to determine their workload as they're operating our aircraft. If we can develop adaptive training that is able to determine the best training regimen for individual users based on their results, based on other information that we have about them. And then finally, we're also looking at workforce analytics. How can we recruit and retain talent in this area? And going back to technical capabilities, machine learning and data analytics are highly relevant to a large number of technical areas, computer vision, autonomous systems. The line is quite blurry these days between machine learning and artificial intelligence. And by applying machine learning to these vast data sets, by extracting new insights and new information, we can deliver great value to our customers. But at the same time, that's not to say that there aren't significant roadblocks for this. We still have a number of compute infrastructure challenges to overcome. We need the workforce in place to be able to do this. There's a vast shortage of data scientists right now. And there are a number of other practical limitations that have to be overcome. You hear the singularity mentioned quite often these days, and while that's something that we might move towards, we're still not at the point where a lot of people have this perception where I can take my data set, I can dump it in a bucket, I can turn the mixer, and out comes my answer. We still have to have a huge amount of collaboration between people who know the data science, people who know the domain, and the end user or the customer. Without domain expertise to really be able to identify what might be relevant in the data, what the false signals might be, what the useful outcomes are, data science will be very difficult to use effectively. So I think I'll cut myself off there, and we'll move back and I think discuss some of these use cases. But move on to you.
Okay. Ooh, this microphone's kind of loud. I'm Melanie Lorraine from Boeing Company, and I'm working in a transition from engineering to IT to structure and integrate this data to make it usable and to be used for business intelligence and analytics. So it's been, I transitioned and started this initiative. The data warehouse, for those of you who's not familiar, is basically kind of like Costco or Walmart, where all the different type of data exists, but we kind of bring it into a centralized organization. We compartmentalize to alike subjects that you can kind of combine and integrate the data for it to get a meaningful insight out of the, as Dr. mentioned earlier, converting data into information. And the difference between the business intelligence and analytics, the way we have defined as a taxonomy is that business intelligence is more of a report, metrics, and dashboard, whereas analytics is looking for a more meaningful, insightful pattern of the data, where we're going to be then making to support the decision-making process. So that's kind of how we have defined. So the history of the data warehouse, the philosophy of this analytics started back in 1989, 1990, going on to, so in Boeing company, we have a spirited pioneers and entrepreneurs within company. We don't, because we're such a large company, the initiative always happens in the roots up. The creative minds and creative individuals start developing these type of technology in place. So the data warehouse started popping up in the 1990s or so. Each program sites, whether in commercial side or military side, started building the data warehouses that's going to meet their business need, localized per program or by location. We kind of then gone through a transition of merging these localized data marts into integrated data warehouse, where we're going to try to look for information more at the enterprise level, military side, the Boeing commercial side level, the military division level. So it became more of a company's initiative to have this at the larger level data warehouse. So it's not so much the siloed financial data, manufacturing data, quality data, but it is more integrated BDS data, the military side of the data versus commercial side of the data. So there's a movement of this data warehouse and a larger integration has been going on. But data warehouse, the overall concept in the industry as well as in our company, started as financial analysis platform. So a lot of the data was good enough to be a month old, a week old, because that's what you were analyzing. You're looking for patterns and trend on financial monthly basis. Whereas now manufacturing and engineering started using this data and said, well, we're going to need it more often. The week-old data is not good enough. Day-old data is not good enough. When you're moving the airplane from the assembly area to the delivery center, and when you're going from delivery center to delivering to the customer pickup, we need to have a lot of these data real time. And then especially when we're doing any of the testing, you know, airplane performance testing or any of the subcomponent testing, and even the factory machining, we needed to have this information more real time. So the operational data store requirement became more and more prevalent. And so we kind of, in a cultural environment, we invested in this heavy data warehouse infrastructure and cost. We wanted to speed up the data from monthly to 3 times a day to an hourly to try to meet this operational need. But that was wrong platform. You know, there's a different nature, different need to architect data warehouse versus operational data store. So we are going and transitioning from converting what need to be a real-time into a near-time platform in operational data store, whereas a data warehouse, day-old or month-old data is good enough, remaining in that environment. The data warehouse is used for more complex integrated data, whereas operational data store would still have the integration, but they're lightly integrated. So the architecture and the modeling of the data are two different way to structure. So we were using this data warehouse and the operational data store to do these reports and metrics and dashboard to monitor the performance, monitor the schedule to execution, monitor how we're meeting our contracts to the delivery schedule, et cetera. And then this, the analytics requirement was bubbling up because the statusing isn't good enough. We really need to know more than statusing and knowing the monitoring. We want to know more than reporting what happened. We want to go into more proactively looking at the information predictive-wise and proactive-wise. So we basically evolved this platform that was set up for the reporting and metrics, and we're evolving into this analytics platform. So in order to do this analytics, big data, as being discussed in here, is part of expansion of this portfolio of data management. So we have a static data and already large, very complex data that's integrated. And it's great, because those data is already available and ready to use. But in analytics, what's happening is you need to supplement and complement what's in structured environment versus all this new data that can be grabbed through internet, through the national publicized data set, international data set, that you can complement your analysis with more and more data. And when we're producing the analytics results, we're not looking at just the past history. And so what's happening is that there's a lot of dynamic expansion of this database that was not a requirement before that is kind of coming up. So we talked about variability of the data, different types of data that needs to be integrated and be serviced and served. The other thing is, it used to be in the platform where it had to be very controlled, because we are dealing with the commercial and the military data, which can be considered sensitive. So it has been, the data access has been very controlled, and to gain a data access to the non-data warehouse environment, even within the data warehouse environment, require a lot of security restrictions and profiling, a lot of administrative work that kind of went with this. So in order for you to be a data scientist or analyst wanting to look and expand your data and analytics capability, you needed it to get a lot of gate to go through to even access the data. So what we're currently trying to do is, when we were setting this new analytics vision for the company, we are looking at it from going from the what happened to what's going to happen. So hindsight to the predictive, proactive model of the data. We want to have the data to be actionable. We had mentioned that we want to convert the data to the information so it'll be meaningful and the information can be used. What we really want to do from the company perspective is not only have the information be useful, but because of it, we are changing our behavior and processes and improve the way we run the business and the way we make the decisions based on the information. So we are enabling a lot of these proactive and collaborative environment, as well as self-service capability, the way we call it, that based on your profile, you would have an access to so many ranges of the data that crosses your normal form of just a vertical silo data. This is going to let you go across enterprise-wide, because when you're trying to look at and doing a problem-solving issue, such as we are looking at a defective part that has a very high non-conformances, or the component of the part that is constantly rejected but end up being used as is, because when you actually put it together, it works. Individually, they may fail, but when you put it together, it works. So in order for you to allow that kind of analysis to happen, it has to cross multiple disciplines of the data. So we may start with the quality, manufacturing quality of the data, that it has to evolve into the engineering data, and it has to go through a supplier management data. So it's never a one single vertical silo when you're really diving deep into the analysis from the business perspective. So we are allowing these infrastructure and constantly evolving and updating this infrastructure for us to go from the data, the concept of the data warehouse, to the operational data store, to this real-time streaming big data, parallel processing, as mentioned in Hadoop and other platform, that it is going to complement portfolio of our data management as a company. So that's kind of high level what's happening. Analytics also can be treated as either one slot, one-time analysis, or it can be an ongoing kind of analytics application. So we basically established from the company's competency center perspective a process that can be repeatable and scalable to a different type of analytic solution. So we developed a standard process, and this is very much in line with the systems engineering that I kind of wanted to share. I thought it would be an interesting concept for us to think about. The way that we allow is that we allow the data exploration and discovery is a very important part of the analytics. So we allow that to happen, and we built in as a part of the project plan. So the very first phase is the data discovery, the requirements gathering. And in analytics, requirements gathering comes like reduce our safety component by 50%. Reduce your non-conformance by 25%. I mean, that is a requirement. That's pretty much a good place for you to start. You don't need to get a very detailed statement of hypothesis defined before you dive into the analytics, because as you discover and learn about the data, your question's going to keep come up, your hypothesis is going to be developed, and you're going to be continuing. It's a very iterative process. So, so we start with the requirements gathering, we look at our data exploration, and then we go through 3 iterations of development cycle. And the way that is determined is that the goal of this is that you want to fail early. You want to be iterative, but you also want to fail early. So you do the first phase of the design development, and you come up with all kinds of variables and assumptions that you want to test. You literally throw 2,000 variables into this predictive model and then see what bubbles up. You know, you let the machine do what it's good at, and we let what it's good at. Recognizing patterns. So we kind of combined the machine's capability, we combined the human's analytical mind, and you put these solutions together and you just let it explore. And that's usually how our first development phase happens. And then after that, phase 2, each one of these phases after your development completes, you go through a review cycle with your customer and your business partners, and you decide whether are we on the right path. Do we continue? Do we want to trim down? Is there any other influential factors that we haven't considered that we need to add to this analytics portfolio? So you basically continue to evolve, iterate, and expand. And then, but the thing is, the thing that I mentioned about failing early, you do want to know and explore as much as you can and fail early. You want to know what doesn't work and what should be eliminated or excluded up front. And then when you're doing through the iteration 2 and iteration 3, you're pretty much fine-tuning. You know, you are supplementing and you're fine-tuning to kind of finalize the results. So by the time of a 3rd iteration of the development is done, your model is going to be in a, you know, everybody knows the evolution of your decision. Everybody knows evolution, what it can and cannot do. And as I mentioned, it's not just pumping out the predictive results, which is statistical value, but you're making a process decision. Once you get these value, what are you going to do with this information? How are you going to change your business process so your non-conformance gets reduced, your productivity goes up, your bottom line profit goes up for the business? So that's kind of the whole full cycle. And then after the 3rd iteration, then you go into the implementation decision. And that's when you not only implement this analytics model, but you are implementing the business process changes that's going to be using these results of the model to improve your business. So that's kind of the overall process that we go through. I just wanted to quickly summarize the high-level architecture. As I mentioned, that we started it with the data warehouse and ODS platform. We're expanding into this big data, parallel, massive parallel processing, as well as the cloud architecture. And there's a lot of security issues that we had to go through and deal with, and still dealing with when it comes to using a cloud architecture, because our data are very sensitive, and we do have to have a very restrictive security guideline that has to be imposed in this environment. But we are testing it out, and the platform is actually set up and we're now ready to explore and jump into that environment. That's pretty much where we're at from architecture. And then the analytics type, we look at the visual analytics. Visual analytics is very highly effective in engineering side, where we're looking at the clearances of the different wiring and making sure that as we're building and designing that it doesn't cross, where the non-conformances are detected, which part of it, not only the surface and the location, but outer surface, inner surface, and the in-between, so you know where the patterns of the defects or rejects are happening, so that you can kind of focus and concentrate. So the visual analytics is very good in that way, and also it's good at giving like quick Paretos of the massive amount of the data and summarize it really quickly for us. So it makes us understand the data quicker. So in average, our group, when we receive a new data, it takes about an hour or two for us to kind of explore and visualize this data, for us to kind of detect the very high level patterns of this data. So visual analytics is very effective for you to narrow down the areas that you need to kind of focus on. In text analytics, we are very effectively utilizing text analytics. And in here, what we're looking for is unstructured data and looking for common structure and structuring unstructured data. So that's one of the area that we use text analytics. We also use text analytics to look for the pattern and validate what's in the unstructured text versus what's in our structured data environment. So if you have categorized of the data, such as your defect type, process type, and then a bunch of description with the nulls. So what we do is we basically train the data to read, and if these type of data is there and these type of descriptions are there, that's the pattern. So the text mining algorithm basically would split out, these are your recommended category of all your uncategorized data. So it really improves your data quality. So prior to utilizing these type of text mining architecture and technology, what we've been using is making decisions based on 40 to 50 to, in some case, 60% of the data, because rest of them is uncategorized, only with a description, but no categories in there. And we were making our business decisions based on that 40 to 60% of the data. But when we applied this text mining capability, we were able to utilize and get the data up to like 90 to 95% of categorized structure, so you have more informed decisions. So we utilize, and the text mining, the technology that we're using, the Boeing does have a lot of research and development in this area, and we do have a lot of tools and capability that was not available out in the industry. So we are early adopters of these areas, and we're utilizing a lot of this text mining, pattern mining technology. And the last area that the type of analytics that we do is predictive analytics. And in here, it's more than just forecasting. It is more, we look at things like the tools. What are the likelihood the tool's going to fail prior to the expiration date? And as John mentioned before, what are the parts that's going to be failing prior to the service expiration date? So we kind of look at predictive models so that we can do some more proactive. We are in the type of examples also in the big data analytics, because we've been doing a lot of these disciplined analytics approach in manufacturing operations, supplier management area. It's kind of interesting when John was mentioning, because a lot of the same targets that we are looking at in Boeing is also being looked at in the Lockheed area. But it is the manufacturing, the operations, supplier management, and in engineering in flight science area has a huge interest. We want to look at and do some comparative analysis in the CFD data with the wind tunnel data with your flight test data. So there's a lot of a strategy and opportunity for us to kind of have not only analytics from the point solution, but overall strategy of integrating this back-end data, having this data be available for us to do that kind of comprehensive analysis. And that's where our big data analytics come in, because the type of data that we're using in engineering are in petabytes. It's huge amounts of data per engineer, per analysis. So these type of large data is not easily done in your client or even in a cloud localized architecture area. This needs to be a bigger architecture and what we consider as a big data. So a lot of the architecture decisions for the big data is happening in an engineering area, supplier management area, where we're looking at, we have in commercial side, we have contracts that is just the service contract, you sell the airplane and be done. And then we have this kind of gold platform maintenance and service area where we're taking care of your maintenance of your aircraft. So for that type of different levels of service that we do have available, we do need to have better predictability of failure and the maintenance and the service of these aircraft. So that's another area. The third,
I'd like to make sure we have time for Nikunj also.
The last area is a sensor area. So the sensor area that we're looking at is in the testing and the flight data, that's instrumental data that's coming in, as well as the factory automation, all the machine, the robots and factory, its performance data that's coming through. So these are the areas that we're kind of expanding into the big data.
Nikunj?
Oh, thank you. There was a set of slides, I think, but I guess, go ahead and get started. Oh, okay, yeah. So, yeah, I'm Nikunj Oza. I'm at NASA. I'm a non-essential government employee. No, sorry. I'm a leader of the data sciences group. Sorry. Indeed. But yeah, so the data sciences group is where we perform research and development of data mining algorithms. Certainly we try to use as much in the way of open source established tools that there are and take what is on the cutting edge of data mining research, but we also do research and development in-house of these algorithms as needed for NASA applications. It's actually both in-house and through various partners that we fund at universities and in industry. The algorithms that we use, of course, they are data mining algorithms, kind of in contrast to model-based algorithms that tend to be physics-based or the like. We want to utilize, of course, the massive amounts of data as we've been talking about. We all have the intuition that there's something useful that we can learn from that, and so that's what we would like to do. The sorts of algorithms we implemented are for anomaly detection, text mining, classification, regression. For NASA applications, we of course all know about aeronautics and space exploration, the various engineered systems that are out there, but we also do significant work in earth science, so this is mostly using satellite-based observations, but to some extent also airborne and ground-based. Also space science, utilizing the results of, say, platforms like Kepler and its observations. The projects that we work on are either directed by NASA, kind of top-down, so where there's the determination that, that data mining, data sciences is needed for that, and therefore we're directed and funded to do so, but we also do get some projects through competitive selections. We, of course, maintain close collaboration with domain experts, which, as we've discussed, is quite critical here. Not only looking at the data side, but there is what is the meaning in that data, and that's really where the domain experts help. And more specifically, I'll discuss a bit about the data sciences for aeronautics. I mean, a key challenge for us here really is the heterogeneity of the data that we work with. So say for data that's recorded on board the aircraft, we have discrete data representing things like autopilot modes, switches that pilots press, and the like. We have continuous measurements, things like altitude, airspeed. These aircraft, of course, do not operate in a vacuum. They do operate with other aircraft in the airspace, and we need to make sure that there's appropriate interaction between these aircraft. So that's where we look at radar track data. And then we also do have reports, text that describe these flights. These could be like aviation safety reporting system that was mentioned. There's maintenance reports. There could be other things. We also are dealing with multiple timescales here. So a lot of what I described really with the aircraft, you might think of it as involving an individual flight and what is recorded on board. So what is happening at the second or minute timescale. But there are also things that happen within the span of a day. You have issues involving, let's say, ground delay program, ground stops. How does that impact traffic before and after? Maybe should the ground delay program or ground stop have been implemented at a different time? There are things that happen over even broader time scales, like months. Maintenance issues happen over the span of months. It could be even longer, even years. We're starting to look now at what we informally like to call before and after studies. So how does traffic change at an airport after you implement something like performance-based navigation? And we're not necessarily just looking at anomalies at individual times. We're looking at, let's say, anomalies or issues that happen over this kind of a long time scale. So it may start with something that's perfectly innocent, but where you get to more and more anomalous states. Most likely you will recover, but maybe there's a chance you get into, say, like an incident or an accident. But that's happening over all of these time scales. And that's why, and this is, I guess, my attempt at bringing a bit of controversy here, I guess, that I dislike the phrase big data, actually, because even though we do refer to the 4 V's, or perhaps we'll get to 7, I think just the phrase big data inherently emphasizes volume. I get asked about how much data we deal with more than anything else. Whereas, at least from my perspective, the most challenging aspect or aspects that we deal with are the other V's. I think volume is actually probably the least challenging aspect we deal with. The variety, the velocity, the 7 or God knows, or the remaining 6 or God knows how many other V's there may end up being, are the biggest challenges that we deal with, and this is just kind of one description of that. That's actually the extent of what I'd planned.
Thank you very much, Nikunj. So what I'd like to do now is turn it over to the audience to see if there are any questions or comments that we should begin with. Yes, sir.
I'm Art Tank. I'm a Lockheed Martin fellow out of aeronautics. And big data is, like you said, disturbing to me because it's so nebulous. I work in a very finite world, right, wrong, black, white, engineering, do it right. And so big data has been this has been a very valuable session for me. So because data can be interrelated, in fact, I think you're betting that it is interrelated, is the data structure, architecture, does that affect the answers that you get? Do you guys ever resort your data, ask the same algorithms, and see if you get different answers?
That's a very, very great question. Was there more?
And there's a part B. And then, in all seriousness, this sounds frivolous, but it really is a quite serious question. How do we learn how to ask the right question of the data? You guys mentioned iterative, and Melanie, you answered my third question already, but it's really important because if I have to create the data structure, the architecture of it, but that decision of the architecture might affect my answers, and then I'm not sure how to ask the question, it sounds like my process of interrogating the data becomes iterative. Would you all kind of address that? And Eric, you're the educator. You might have insight into this, whereas these guys are the applicators. But I'm interested in the answers. How do I make sure that my data is correct as in architecture, and how do I ask the right questions?
So I'll briefly talk about the first part of your question, because I think it gets really to the heart of dealing with distributed data systems. So another way to phrase it is, let's say that we have data distributed across a couple of different platforms. Let's say you've got 100 different computing platforms and you've got data partitioned on it. You run some computation on it and answer A comes out, okay? You write down answer A. Now, I think what's underlying your question is, if I reshuffled the data between those 100 systems, or I re-architected it or something, and I ran the same query, I think you would want answer A to come back. But sometimes answer B actually might come back, and B is not equal to A. And this is a fundamental problem with dealing with distributed systems, particularly if you do what's called meta-modeling. So this is the idea that you say, I'm going to run my algorithm. I choose my algorithm X. I'll run it on data set number 1, number 2, number 3, up to number 100. Now I'll do a meta-analysis of those 100 models and divine some truth out of it. The problem with that is that, for example, for anomaly detection problems, what's anomalous in the first data set with respect to the first data set may not actually be anomalous with respect to the entire data set. And that's why the answer that comes out might be different. So one thing that we're very focused on is developing algorithms which are provably correct. And what I mean by that is these algorithms are such that if you take the data, partition it across 100, 1,000, or 10 partitions, reorganize it in any way, you're guaranteed to get the same answer as if you had centralized the data. This is so the correct. So that's the repeatability of the answer. Repeatability is frankly not always guaranteed in a distributed system, but for the types of applications I'm describing, for query-based applications, it should be unless you've made a mistake. But for discovery-based systems, it need not be the case. So the first part is repeatability. Now, as far as the verification of it, to check whether or not this answer is correct, that's something that is often done in parallel, or I should say, that's a question that should be answered independent of the nature of the data architecture. So what that would imply is that as you change the data architecture, the answer shouldn't change, and the correctness of that answer shouldn't change with respect to some independent metric that you've put down. So I think I appreciate the question, because when I've worked on problems where anomaly detection comes in, I've seen many papers come through the conferences and so forth, which essentially build algorithms separately, combine the data, and then proclaim that some answer must be true. And in fact, you can prove that that can't be the case. It can be shown that that can't be the case. So there's some very pioneering work going on at Stanford and other places in which they're designing algorithms that are such that you will get the same answer, and the answer will be repeatable regardless of the data architecture that's underlying it. But the caveat is that you have to make certain assumptions about the loss functions that you're optimizing. They need to be convex and so forth. So it gets a little technical there, but I appreciate the question. I'll turn it over to Eric and others for further discussion.
I got particularly interested in the second question you asked. Choosing the question is, as you said, an important factor of success. And what I wanted to raise is that the data and the question are like the chicken and the egg in the following sense. Shall I ask the question first and then go and get the data that I need? Or shall I go get the data and then figure out what kind of question I can answer? And I must say that as a researcher, I fall clearly in the second category. So give me the data, I'll tell you what questions you can answer with it. And however, yes. Yes, absolutely. And one of the things is that, going after the data and then figuring out what question you want to answer runs counter to traditional engineering. I mean, people would prefer to first, have like a more organized plan of doing things. However, with the massive amount of data that we have now, really, it's about, not only it's about answering the engineering questions, but also exploring the possibilities. And exploring the possibilities is like, if you were to formulate that as in a sort of traditional state space kind of environment, it would be to say, and I certainly repeat myself from the previous, from what I said before, which is you got data set. In fact, what it tells you is it tells you the more data you have, the more you're likely to discover like some new mechanism that makes the underlying system run. And you're going to say, of course I know how it runs, I designed it. Well, that may be true of many man-made devices, but even some man-made devices, nobody knows how they run. For example, the air traffic control system is sort of a continuous discovery process about how people actually manage to get the things done. So what you get is this thing whereby, on the one hand, you can start from the physics, then say, okay, here's the data I need in order to like fix or like tune up my physics, okay? Or on the other hand, you say, well, here's my data, okay, and what is the physical model that could actually fit behind this data? And then maybe by keeping your eyes open, discover, oh, there's this thing here, there's that baby that I was about to throw away with the bathwater that actually appears there that I didn't know about or I did not suspect I could even get. And the question is, where do you decide that you're done? Okay, where do you decide that you're sort of gone? You've used all the data, you've used the data to the maximum possible extent to answer your question, or that you have used, or that you have used the data to sort of decide that you can answer no more questions than the one you've asked. And this is sort of a very traditional question arising in many different disciplines. Again, I'm going to cite my discipline, which is the following. On one hand, how many data do I need to answer the question? That's like, well, how low can I get my covariance matrix before I decide, okay, it's over? All right, that's the other question, which is how many questions can I answer with my data? That's the database modeling paradigm. And it's the same question as the very precise one that arose in control, which is how many states are there in my model? And by the way, the second question is still subject to debate. You never know if you have enough states or not. You always have like these very ad hoc criteria that are based on a collection of singular values. And at some point, one of them drops down to like some ridiculous low value, and so okay, that means it's not significant anymore. Okay, but bottom line, in terms of deciding whether you're done with the data to answer your question, you're done with the questions that the data can talk about, at some point there is sort of irrational level that will lead you to make that decision. People try and make it more rational, but even for the simplest cases, the questions are not fully answered yet.
Another question?
Yeah, maybe it might be a little bit naive, but I'm really trying to get my head around this whole big data concept. Let me tell you where I come from. Just recently retired after 30 years of sustaining intercontinental ballistic missiles. And the way that we had a lot of big data because, and we still do, what happens is you've got to be able to predict that that missile is going to work when it's going to be launched. And it's in a vault buried up in the northern tier, and there's not dozens, there's hundreds, and there used to be thousands of these missiles out there all producing data. So you have the ability to take a look at, for instance, all the data streaming to you constantly from the guidance system to make predictions about whether your system will launch when it's asked to, whether it will be reliable when it does launch, whether it will be accurate. And on top of that, of course, it has to be nuclear hardened. If you meet those 4 criteria, then you've met the mission requirements. So all the data you're looking at flows back to those sort of KPPs. And so you know exactly what you need to look at, even though it's a vast amount of data, in order to answer those questions. Now, other pieces of the missile, like the downstage, they're not producing data like the guidance system. So you have to periodically pull them out, test them, and get reams and reams of data from those tests to describe to yourself, okay, is it degrading? Will it be available if we use it? So it all seems very deterministic to me, but what you're describing is almost looking at the data in order to frame the question, when in fact, if you're working with a weapon system, you know what the question is. Is it going to be available? Is it going to be reliable? Is it going to be accurate? And will it be hardened against nuclear effects?
So I think in many cases, what you're saying is absolutely correct, that the questions are established. But I think one of the things that the data analytic approach can give you is new ways of answering those questions. And I think in decision support systems, the idea is that it might also reveal new information, new correlates that can help you understand the predictions that are made and the reasons why those predictions are made.
A good example of that would be the fact that when you design it, you've done a particular FMEA, and after a couple of decades of data, you realize that, oh, you could refine that FMEA. There's other failure modes we never thought of. And if you have your mind open to seeing those in the data, you'll see them. But if you're not looking for them, you won't see them.
Right.
But maybe that's part of what you're talking about.
Nikuj?
So a lot of what you are saying is from streaming data perspective. What you can create is actually visualize small multiples of the patterns with the tolerances, so you know as it's coming in whether it's in tolerance, out of tolerance. And if it's out of tolerance, you want to know at what condition does that become out of tolerance, and you want to do a deeper analysis on those. So you can, real time, what you're doing for the most time is monitoring, the peaks and valleys and in control, out of control state.
Yeah, what we found most useful is, like you say, you pair up the data experts, the statisticians, and the engineers, and then you make the process cheap. So if the engineer says, I need to look at this, then the data person says, oh yeah, we can do that. That's not very expensive. We can just tweak this, and you'll get that data. If you can do that, that's wonderful. Sometimes, though, the answer is, oh, well, that's too hard to do. You want me to sort a list? You don't understand. I'll never sort the list. You know, sometimes you get that kind of feedback, and you have to throw up the BS flag.
Couldn't you want to make
yeah, I think what you bring up really alludes to the broad variety of problems that we really deal with in the, okay, I'll use the phrase big data, I'll go ahead and use that. It could be anything from, the reason we're doing all this, the reason we're bothering with the expense and effort of saving this data and trying to do something with it is because there's something we don't know. It could be anything from not knowing exactly a particular coefficient within a particular model all the way to figuring out that there may be certain circumstances under which the whole model of the system is just wrong. And there could be anything in between.
And I think you all touched on maintenance. We have a very sophisticated maintenance database at the maintenance depot. Yeah. And the biggest deal there is making sure that whoever's entering the data is not just in a hurry and they put good data in. And the way that we got them to do that was to help them understand that if they put good data in, it helps the analysts figure out what's really going wrong, and you can fix the right thing the first time. Anyway, I've taken enough time.
Just real quick, I mean, along those lines, I think what you mentioned as far as it appearing to be a deterministic system is absolutely right. And this is a case where we have to, again, work with the domain experts and look at the models that are already in place and have been reliable. But at the same time, no system that we work with is truly completely closed. There are always going to be factors that we're not able to account for in our models. And so if we're able to collect data on those factors, though, then maybe we can use that to see what other influences are out there that maybe we should be incorporating into our models somehow.
Thank you, Ashok. I actually have a question that probably follow up on what we're discussing here. It seems to be a repeating theme is that we have a gap between traditional engineering that is largely deterministic, and then you have now a new generation of people who are doing this data science one way or the other, which is primarily statistics based, and primarily in a way a lot of the tools that are used are blind to the engineering models. Not all of them, but I would say vast majority. That's true. And so you have this gap, and it's a cultural gap, and it is a gap between these two type of people. It's a personal gap. And I would like to get some insight. I know that, Ashok, you were kind of on both sides, if you want, because you were at NASA and now you're with Verizon. I would like to get your input. And then since I will take I want to know kind of what the attitude from the practitioners in Boeing and Lockheed Martin in terms of how they deal with this, how many data scientists you have at the moment that you would consider both Boeing and Lockheed Martin, how many of them number-wise, and also whatever you have, do you consider that this is going to be dedicated teams of data scientists, that kind of tiger teams that move from one project to another, or those are the people who are embedded effectively into the particular projects? So kind of in terms of interaction, that's I would like to ask that question. So first you, Ashok, and then maybe.
Thanks, Vitaly. So this is a critical issue that I think those of us working in computer science, those of us working in aerospace as two very large fields need to address. There's no doubt that determinism and the power of physics, to put it bluntly, that we take advantage of when we're building engineered aerospace systems, it's culturally, it leads one to a culturally different way of looking at the world than what you see in computer science from the database perspective, and even there to the machine learning. So I'm more of a machine learning person. There we tend to think of things more in probabilistic terms, probability distributions and propagating probability distributions. And the beauty of that is that it does lend itself more to physical modeling, as you well know. But if you simply view things as bits and bytes, and items residing in a relational database or some Hadoop system, then it's even further divorced from model-based. So my personal hope is that forums like this, the journal, and many people's works are going to start bringing together the following. The fact that the physics can be informed by data, and that the data can be informed by physics. Now, physics being informed by data is much more than, for example, learning the coefficients to a set of differential equations from data. That's an important activity. It's been done, and I think people will continue to do it. But I think more interesting than that is to say that the machine learning algorithms could uncover new physical phenomena, kind of like Eric was describing, something new, a new approach, a new way of understanding the behavior of the underlying dynamics that could then be used, and perhaps used in the best case to discover new physics, or in another case to simply have a better understanding of the model. If you think about what goes on in large economic systems, for example, in stock trading, for instance, there's no real physical model that says why things might be bought and sold, right? If you look for those models, you find that they're AR1 models, autoregressive models with one delay in them. It's actually true to be the case. So those kinds of models may not be as informative. So I'm hoping that these types of forums will bring these two areas together, and that people in this audience and your colleagues will start to think about how to take advantage of these analytical techniques in the more physics-based works that you do, and vice versa. I also believe that some of a lot of the discussion today has been more along the lines of human analysts analyzing data. In the old days, we would have called this data analysis, right? Some fancy data analysis, but it's that. But I think that in aerospace, we can take it a few steps farther than that, to say not only are we going to build automated systems to analyze the data, but most interestingly, we can then deploy them to take automated action. So now the aircraft or the spacecraft is understanding its environment, and then it's taking a decision based on its understanding of the environment, and then it has the ability to monitor it. So then it becomes a full outer loop, closed loop system. And I think that would be very interesting. So does that address it? And then Eric or others?
Vitaly, so.
Oh, yeah.
Yeah.
Please.
Go ahead.
Right. So, I mean, this is an extremely important point that you bring up, and there are two conflicting ways to look at it. You can look at it as here's the data, here's what it's telling me, so there's no argument with that. And then there's the way of looking at it of, well, I'm just going to model this on my system. I'm going to follow the traditional method of manipulating one variable at a time, theorizing what's going to happen, and looking at my output. The problem when we begin to incorporate these larger amounts of data is you can't really manipulate a single variable at a time when you have thousands of variables that aren't necessarily independent. So it's definitely a combination of those methods that has to work. The best example I have of this goes back to brain computer interfaces, where they sell these headbands that have two electrodes that go on your forehead, and you're supposed to be able to concentrate to control things with it. And it works, but at the same time, most of the time, what is actually happening is it's just reading how much you're going like this. If you squint your forehead muscles, that completely overwhelms any neural signals that are in the area. And without a knowledge of the underlying neuroscience and the physical systems that are going on there, you have no idea that that's happening, that you're not actually getting what you're looking for. So there are a number of pitfalls you can fall in if you just look at it as bytes and numbers. So what we're doing at Lockheed Martin is we do have data scientists. We have domain experts. We have certain problems where they're working together, collaborating on these issues. And then we also have a strategy where we need to be able to bring the data science tools to the people with the knowledge of the system. so that they can use them to refine their model, to improve what they have, maybe be able to better visualize the data. That's another important aspect of data analytics, is not necessarily providing the answer, but just being able to provide the information to someone in a format that allows them to better understand the question or the answer. And beyond that, you know, again, data scientists are great, domain experts are great, them working together is great. Kind of the unicorn out there is the person who knows data science and knows the physical systems. And ideally, that's the person you want. And you know, there are resources out there for learning data science, learning how to use these tools in a basic manner. There's Coursera. Andrew Ng has an excellent machine learning course that can help train people with domain expertise in using some of these tools. So we have a number of approaches that kind of sums it up.
Okay. Data science and analytics is kind of the way of thinking. It's not necessarily a title. So the way that it's been practiced is that there is a data scientist that's embedded in their current jobs, and they do this whether they have the title or not. What we are trying to do is try to identify people who have the business process knowledge and then pair them with the people who have a data scientific tools knowledge. So we have this pair analysis team that has what we call tools people with the SME, the process and the data SME, with the technologist, and we usually form a team for us to kind of attack the problem. We have, because we are a large company, we are trying to centralize and core this up at the core level. So there's an initiative for us to kind of bring this up at the enterprise level. But right now, so in IT, we have a group of data scientists. And in functional side, we have groups of data scientists in the military side and the commercial side. So, and that's including manufacturing engineering, not just engineering, hardcore engineering. So we are in a process of kind of having these analytics, COE kind of concept, so that we can partner three-way together. So the IT data scientist would have certain RAA, the research data scientists would have certain RAA with the SME, which is the business process owners and functional team, and trying to work it together. That's our current strategy. And as far as recruiting the data scientists, a lot of a real good data scientists are those functional SMEs and business SMEs that's already embedded into the process. So don't look out far. You may have those right skilled people in your own organization.
So I've found kind of, I guess, a contrasting view that actually it seemed I found the most value in having data scientists who don't know the domain well, because they're not bound by the domain. A lot of why we're actually being brought in to the particular area is to discover something new. And we certainly explain to the subject matter experts that, you know, we might initially come up with some stupid things, and they are patient with us. But there is value in the data scientist going through this process, seeing some kind of data, thinking, okay, here's some algorithm or set of analysis steps we can do to get some result that maybe turns out to be useless, but at least it lays out to the subject matter expert what is the set of tools we have available, what we can do. And we find that often inspires the subject matter expert to actually come up with something better then, because that person sees something and can then poke holes in that, make some adjustments, and come up with something better. It just kind of gets the paralysis of what to do first out of the way just by having something there.
Next question.
Rolls-Royce developed a algorithm which was looking at maintenance reports to try and classify whether a certain maintenance action was actually a no-fault found action or some other type classification. I'm very interested to hear what the panel would say regarding trying to generalize that across different organizations, because you may be aware that different organizations have different phrases and codes and ways of saying that they didn't find a fault. So it could be difficult to instinctively find out whether a certain action was no fault found. And I'm especially interested to hear what Nick Oza would say, given that he was saying about looking at maintenance actions and consequences over months and years in that regard.
Nikunj?
Could you repeat the last part of that question? I had trouble catching that. I'm sorry.
Well, look at no fault found across from maintenance reports, try and identify whether a maintenance report was actually saying that there was no fault found in that instance. And especially interested because you were saying about how you were trying to use data analytics to look at maintenance actions and the consequences from those actions across different timescales out to months and years. Well, it's one of the things that a lot of people in aerospace will say that no fault found is a really big challenge, and they'll start talking about how when they take something out and they don't find a problem with it, they'll replace it or they'll do shotgun replacement, they'll switch things over from one bus to the other, maybe it's the connectors that are dirty or something, and try to track down what it is exactly that's creating the in-flight anomaly that's causing the report that is triggering the removal of some line replaceable unit, which is causing this cost to no apparent identified fault. So I may have rambled on a bit there, and it may be confusing what the original question was.
Yeah, I guess in our case that's I guess the biggest thing is really been kind of, don't know to what extent this ends up going to your question, but when you were mentioning that, it really reminded me of an issue of just like different ways that end up kind of phrasing the same problem, or maybe even you get different people's perspectives. I mean, like maybe they're like say different maintenance personnel, or I'm thinking of things like an aviation safety reporting system where sometimes you may get a description of the same problem from the perspective of, let's say, a pilot versus an air traffic controller, and then they superficially maybe read like very different reports, but they turn out to be describing the same issue, so it's maybe kind of different manifestations of the same basic problem. So it's like you're not really finding one problem. It's really, okay, here's kind of the root cause, which you may never really know, and then there are all sorts of different ways that that effect shows up, and you might see kind of reports or snippets that describe these different things that are at the bottom that really relate to something that's at the top. And kind of as you alluded to, I mean, they may not even be at necessarily at the same point in time, right? You may have, like, I mean, it's typically with maintenance, it's going to be, right? And it's an action that was way in the past that is then leading to something that could be even way down the line.
So that kind of data variability can also be dealt with through natural language processing techniques. So one approach is, as you're pointing out, to dictate that one should use certain language, but in some cases it's not practical, or it's just not followed, thus leading to variability. And oh, that's true.
Should we answer to that, or should we answer to the next?
Yeah.
Okay. I do have a comment, so let's come back to you. Okay.
You want to next question?
Sure. And I was trying to stand here craft a question or two on to represent a little bit of unease I was feeling as an engineer. You know, the more terms that we add to the model, you know, that pesky little E term on the end, you know, in our minds just shrinks and shrinks. As a statistician, I know that, you know, we're going to do some closed loop control or things like that. In reality, the more terms I add to that model, the more likely it is I'm going to make the wrong decision or choice. So I guess the couple questions I have, the longer I work, and I'm sorry, I'm just a unfrozen industrial engineer in an aerospace world. That the little understanding of measurement error, and do you see as the processors of this big data, do you see our ability to take this data and process it? Are we outstripping our ability to actually take good data, or do you end up having to spend a significant amount of that time developing the algorithms that detects errors in the algorithms that's really due to measurement systems error? Those are my two.
So your point about increasing the number of variables being a problem is a big issue in machine learning. It learns to something we call overfitting, where, you know, say you're watching a baseball game and they give you some statistic that, you know, this guy, when he's batting at this park at this time of day with the wind blowing in at 7 miles an hour and all these other factors, he's hit 2 home runs. You know, I don't care about, you know, if you filter the data 50 times, of course you're going to get a result like that. So what we have to be careful of doing is being sure that we get an accurate model that's generalizable, so that we're able to predict future similar events that are not necessarily precisely the same across all of these variables, but they're similar. And to your other point about the data, you know, being able to properly clean and extract the best features from the data is to me the key of getting good data science results. You know, people talk about the algorithms, the deep learning, the random forest, all this other stuff. You know, that might slightly alter your outcome, but not as much as having good data and extracting good features. And this comes down to a lot of important decisions. You know, if you have time series data, do I want to use the raw value? Do I want to use a moving average? Do I want to look at it in the frequency domain instead? If there are missing values, do I want to drop that sample? Do I want to replace it with the average? Do I want to set it to 0? So there are a lot of factors here in how you manipulate your data and get it into that nice tabular sample by feature format that can greatly affect your results. And then once you do that, again, you've got to be careful to not overfit to that large number of variables.
And that's we mentioned about IT teaming up with a data SME. That's very reason why. We need to have a person who needs to generate the statistical model and evaluate and help us interpret that. But we also need a functional team who knows what that means to the data. So it's not a standalone activity. It has to be context, and the subject matter expert and the data expert and the process expert needs to understand what this means in data when the results come out. And the tools give you the variable and the numbers and the results, but it's the SME and the knowledge of the business that's going to make a decision to accept or reject that information. Oh, you mean from the, yeah, you mean the analytical results once you get it? So I think I'm going to go back answering your question, because the way that we look at it is, I mentioned this iterative approach. The analytics usually takes inductive and deductive, and it kind of flips back and forth. So you want to explore the data without any pre-notion or concept, right? And then you get a certain type of results back. Then now you have now based on the results, you have a certain set of questions. So now you formulate a hypothesis. Now you go through answering, proving or disapproving your hypothesis about the analysis results that you got. So you kind of go through this iterative approach. You take what the results of the analytics say, and then now you are bouncing against your assumption and your knowledge about the results to say, is this really what I think it is? You create a hypothesis. Now you go to the deductive reasoning and methodology to get your hypothesis validated. So then if your hypothesis is not correct, you come up with an alternate hypothesis and then you test. This didn't fail, so this was not valid. My assumption was not valid, and what I thought the data was telling me is not valid. Then you go through the secondary hypothesis testing. Now let's see if this data is meeting my second hypothesis. So you go through the kind of iterative hypothesis testing and modification and validation of a hypothesis, and you do flip between inductive and deductive because of that. And that's part of the iterative issues that you have to go through. Because no one model is going to give you a complete answer.
So we have one last question, and then we need to...
Hi, I'm Bertrand. I'm working actually in an airline. And I'd just like to give, maybe for the colleagues here, of some examples we have done in machine learning in the airline, and we've designed internally. And I suppose it's just to give some practical examples to people that this thing is real. One of them was around fuel burn estimation of each individual aircraft and individual engine. So with machine learning and coupled with a physics-based model, so we're talking about proper aerodynamic and propulsion model, we were able to basically provide or create performance databases that are used in path planning, flight planning, for each individual aircraft and each individual engine. And that resulted in basically an aircraft flying the same speed schedule, cost index, actually flying different speeds and altitudes. And the order of magnitude in terms of fuel burn effect is about 0.5 to 1.5%, so it's pretty substantial. So it's machine learning is something that can really help your business, your bottom line. Some of the other examples we've done is in predictive maintenance. In this case, it was in the A380, Airbus A380, where we were trying to reverse engineer the ECAM logic, which is equivalent to ICAS for Boeing. So interesting thing where it's ECAM is based on human algorithms and logic. So using machine learning, we're trying to find out what logic is driving it and trying to predict if there is a class 1 fault appearing, which usually results in an air turnback or a delay in the aircraft. So it's very practical, and it was based on rare event type modeling. And the difficulty is, of course, is to get the maintenance ops center to agree and to believe the system. If you get a lot of false positives, it means if you get a very high percentage, you will not get buy-in from the MOC people. Some other little anecdotal things were, we were trying to predict the failure of the IDG generator on the 747, and some interesting things came out. For instance, people usually in the maintenance world reason in ATA chapters. So using a machine learning where we just mix everything together in a big soup, found out that one of the early indicators of a failure of the generator was the captain's clock. So there's all sorts of examples, real-world examples, which I could give you, where data mining, we've used data analytics, data mining in the airline. And I suppose the key to it is all this, you have to mix both deterministic physical models with this new generation of big data. If you don't, then you will not get good extrapolation. For instance, the example I was referring to before about the fuel estimation models, what we've found out is that the aircraft is always being held in the same optimal space, whereas our models are telling you that the aircraft should be somewhere elsewhere. So if the models were not based on a physical model, initially with, of course, a data mining layer to it, then we will not be able to extrapolate. So it's something that is real, and it's got a lot of power, and we've used it to quite a degree of success in the airline. Thanks.
Thanks very much. So I think we need to conclude our panel. Thank you very much to all panelists.
Can I just mention a quick thing that kind of connects a few of these questions?
Please.
So the physical system and the number of variables we mentioned, there are ways to identify which variables are important in a data set. But something that, again, working with the domain experts we frequently encounter is if they want to know why. Here's what my model's predicting, okay, why? And that's not an easy question when the answer is, well, it's the specific combination of 300 variables, not really any one individual factor. But that's something that we have to drive towards, and being able to identify what are the major contributors so that we can connect them to the physical systems, so that we can adapt our design processes and close that loop, like I mentioned earlier. And knowing what question to ask, there are methods, again, for, typically you have a data set, you have a variable you want to predict. Sometimes you just have a data set. You don't know what you want to ask. There are clustering methods that can group the data, and then you can identify what the groups mean. There are dimensionality reduction to where you can interpret it in 2 or 3 dimensions instead of 3,000. But again, it goes back to allowing the computer to do what it's good at and crunching the numbers, and allowing the human to do what they're good at, and being able to do this abstract reasoning and to draw causal connections in the data.
Thank you. So thanks very much for your attention. There will be on Thursday, I believe, a paper session that Nikunj Oza and I are co-chairing on big data and analytics. So you're welcome to learn more there. Thank you very much.